everybody. Sorry for the change of time. Today we are 1 hour late, and this is due to avoid the superposition with the conference of the GGI workshop on gravitational scattering in spiral and radiation, which is running now. Many thanks to Mariangela Lisanti to be here with us. It's a little late for the tea break, nevertheless, I'm sure you will enjoy our theory colloquium. So please, Francesco, go ahead with the introduction. Thank you.
Okay, thank you, Stefania, and good afternoon or good morning or good evening to everyone, depending on where you are. It is my pleasure to welcome today's speaker, Mariangela Lisanti from Princeton University. Mariangela got her degree in physics at Harvard University, and then she went to Stanford for a PhD. After getting her PhD, she was a postdoctoral associate at the Princeton Center for Princeton Center for Theoretical Science, PCTS. I wanted to say it right. And after this appointment at the PCTS, she joined the Princeton faculty, where she is an associate professor now. Mariangela's interest in high energy physics covers a wide range of topics in phenomenology, from the phenomenology at particle colliders all the way to dark matter theories and dark matter searches. Today, she will tell us about some recent work she's been doing very recently on the process of data from the Gaia mission, and in particular, what we can learn about dark matter in our galaxy from this data, and also the implication for dark matter searches in our labs. So please, Mariangela, the floor is yours. Thank you again for accepting our invitation.
Thank you, and thank you so much for having me. It's always a real pleasure to join for these talks, especially during these times. It's just wonderful to be able to see people again and have these conversations, even if they're virtually. So I'm planning to talk today about some recent work that my group has been focusing on for the last few years that ties together data on galactic scales, so in particular focusing on data from the Gaia satellite, down to the smallest scales in our labs, deep in mines or under mountains that are searching for dark matter particles. So the talk today will focus on an area of research referred to as galactic archaeology, where we want to try to understand how our Milky Way galaxy evolved to the present day, and then use that understanding of the historical evolution of the galaxy to inform and build a map of the local dark matter distribution, which is directly relevant for any kind of search for dark matter that we would undergo in a terrestrial lab. So there's a long history to using information on galactic dynamics or evolution in our understanding of dark matter, and this just goes back to galactic rotation curves, which are the classic example, where going back to the work of Rubin and Ford in the 1970s and 1980s. The observation that galaxies are rotating faster at larger distances from the center of the galaxy, in contrast to the Newtonian expectation, really started the whole thinking about the dark matter and models that could potentially explain it. Even today, we have so much to learn just about, just from the motion of stars in our galaxy. So, for example, one possible explanation for the flat rotation curve, separate from adding additional matter like dark matter, is to argue that we would need to modify Newtonian gravity. But it turns out that explanations where you have modified gravity, in addition to the challenges it faces in terms of explaining the cosmological evolution of the universe, also ends up hitting challenges much closer to home. So, for example, these theories of modified gravity typically end up predicting much larger vertical accelerations for stars in the galaxy, like the Milky Way, so for our disk stars. And these larger accelerations would translate to larger vertical velocity dispersions for the stars. And this is something that we can go and look for in the data, because the data quality is quite good. So in recent work, we found that the kinds of vertical accelerations that you would need in order to be able to reproduce flat rotation curves with modified gravity is inconsistent with the actual observed vertical velocities of stars. So I think this is kind of a nice example showing like the fact that we still have so much to learn just by looking at the motions of stars within our galaxy. In this case, this is telling us something about whether or not we would be modifying gravity versus adding additional matter to the galaxy. So if we go the route of adding some additional dark matter, we're thinking of this here as just being some big halo of dark matter surrounding the visible part of the galaxy. That the halo itself is extending out nearly 10 times the distance as the baryonic visible part of the galaxy, so quite large. And when we are doing our searches for dark matter in a terrestrial lab, we're really only focusing on a very small portion of the halo. So we're kind of zooming into our own tiny little corner of this galaxy, looking for dark matter particles that are flying around that might hit some target in our detector. So here I'm just showing the Xenon 100 experiment, but I mean, there's a whole host of these experiments that are currently underway in many labs around the world. And what these experiments are searching for is one of these interactions where a dark matter particle from the halo flies through, hits, let's say, a nucleus in the target, or perhaps an electron, causes the nucleus to scatter off. And while we never end up seeing the recoiling dark matter particle because it isn't charged and it's essentially invisible to us, we can search for the perturbation that would occur to the nucleus from this kind of scattering interaction. Now, the rates that you predict for these interactions to occur depend sensitively on both the local velocity distribution of the dark matter as well as its overall number density. So, and in particular, there's a direct degeneracy between the scattering cross section that you would recover for the dark matter interaction and the local dark matter density. So having an actual map of what the dark matter is near us and also how it moves near us is an essential input towards interpreting the results from any of these experiments. Now, there's a long history of building these kinds of dark matter maps, going back all the way to the original work of Oestreicher-Peebles and also the classic paper of Drucker, Fries, and Spergel. So this is kind of going back to the early days, right after flat rotation curve discovery, where there was the idea was, okay, well, now if we are assuming that there is a halo of dark matter, what is its velocity? What is its distribution? And the approach that was taken, which is what's still predominantly used today, is to assume that the dark matter is a collisionless fluid, and you assume that the fluid mass is conserved. And then you layer in some additional assumptions. So for example, you take the velocities to be isotropic, you state that you want to make sure that you can recover a flat rotation curve, and you assume that the whole fluid system is in steady state. So if you combine those additional assumptions with the fluid mass conservation equation, what falls out quite cleanly is essentially a prediction that the dark matter distribution has an isothermal density and a Maxwell-Boltzmann velocity distribution. So this was worked out in full, starting from these papers that I've cited down below, and it's pretty much the standard, what's referred to as the standard halo model. And it's what's used in all analyses today. So whenever you open a paper from one of these direct detection experiments, they are just always essentially assuming this Maxwell-Boltzmann distribution. We're very lucky today to be able to actually revisit these assumptions. So while they've been in place for decades, the quality of the data that we have is such that we can go back and ask whether or not the assumptions going into the model are consistent with our observations. And in particular, what I want to do now is sort of focus specifically on the assumption of steady state. So asking specifically, what does it mean when we say that our Milky Way galaxy is in some steady state condition? And so I like thinking about this kind of heuristically in terms of like a family tree for our galaxy. So here I'm denoting time as increasing as you go down on the slide. And in the lambda cold dark matter paradigm, the way a galaxy like our own grows and evolves with time is through the merger of smaller systems. So I'm denoting that here in the family tree as sort of two smaller circles that combine and then forming the Milky Way as shown here on the left. The example here is an example that's what we might call a quiet merger history. So for example, you have this merger that occurred a long time ago, and then the system essentially was able to sort of sit there, come into equilibrium, and giving us the galaxy that we see today. We can contrast this with a much more active merger history where we would have had a lot of these kinds of combinations of different galaxies, being eaten up by our own, finally giving us the Milky Way, today. And the steady state assumption is essentially assuming that the left picture is what's going on in reality, and not the right picture. But obviously, that's an assumption that's going into the model. And we can ask, well, based off of the data, do we believe it should be the left or the right? And how does that end up, does it validate or does it disprove this steady state assumption that's going into our modeling of the dark matter distribution? And getting at the heart of this question requires a number of advances. So it requires really good data. And we're at a great, we have a great opportunity to address this now, primarily because of the data from the Gaia satellite, which I'll introduce in a little bit, but that's kind of the big shift that happened on the data front. Another important ingredient is good simulations of galaxies like the Milky Way. So including dark matter and the baryonic physics. And over the last decade, there have been really leaps and strides that have occurred on that front that have opened up the possibility that we could sort of understand on the simulation front how all of this should be behaving. And then the third ingredient is data science techniques, because these, data from Gaia is essentially, that's big data, the way it's sort of thrown around colloquially. It's a massive data set. It has over, in full, it has over 1 billion stars. And so mining this data to try to find the patterns that we could then end up using to infer something about the history really involves some the use and application of some interesting and really exciting statistical techniques, many of which have really only recently started to be adopted in physics analyses. And so I think this is kind of it's a fun opportunity where we have all of these recent advancements coming together that we can combine and actually shed light on fundamental questions about how our galaxy evolved, and also the implications of that to the terrestrial experiments and searches for dark matter. So moving forward, I'm going to start with just a general overview of how a galaxy like our own evolves in over the time scale of several giga-years. And this first part of the talk is going to be really based off of simulation. So I'll introduce some of the things that we've been learning working with these hydro simulations. And then the second part of the talk will turn to actual data from Gaia, and I'll show you what we've been able to decipher about the Milky Way's evolution and the impact on the local, what we believe is the impact on the local dark matter distribution. So let's start off with some fun movies. So I'm going to play for you a simulation of a galaxy that's similar to the Milky Way. So when I say similar to the Milky Way here, I mean it has a mass that's roughly comparable to the mass of the Milky Way, so 10 to the 12 solar masses, and is reasonably isolated, so meaning it doesn't have any large galaxies nearby, which we know to be true for our own Milky Way. This particular simulation comes from the FIRE group. FIRE here stands for Feedback in Realistic Environments, and includes dark matter, stars, gas, all of the hydrodynamic physics is included in this. So the movie that I'm going to show is just of the stars in the simulation, but just keep in the back of your mind that we have also all of the information about the gas and the dark matter over the same time period. It's just not included in the movie. So this starts here at redshift 10 and evolves from there. And you can see these small galaxies getting eaten up, sort of falling in, getting totally destroyed, and ultimately all of the material that that gets removed from them ends up forming is sort of concentrated here, and you end up getting a formation of a stable stellar disk, which would be like the stellar disk in the in our galaxy. So let me see if I could play that again. So this early stage is sort of very chaotic. You have a lot of these very significant mergers occurring, but then roughly around redshift 1-ish or so, you have much smaller size mergers, and that's what allows the disk to essentially remain stable up until the present day. So there's a lot of information in these simulations, and what we want to do is essentially go in and really understand how the stars and the dark matter are behaving for these mergers as a function of time, because that'll end up teaching us something about how we expect the dark matter distribution in the galaxy today, to how we can infer that from observations of the stars, which is what we're getting from Gaia. So the simulations are going to allow us to do this mapping from data, which is just from the stars, to the dark matter, which is what we actually want for our understanding of direct detection experiments. So I want to do this kind of piecemeal. So I'm going to start with, we're going to essentially track the life of one of these smaller galaxies as it falls into the Milky Way. So here I'm showing here a small little satellite galaxy that's had the misfortune of coming into our galaxy, essentially getting tugged in by the gravitational pull of our galaxy. And so it starts its process of orbiting in. And in the initial stages, as it's falling in, it's going to be experiencing tidal forces from just the massive host here, the massive Milky Way galaxy. And those tidal forces are going to start shredding up the satellite. So it'll pull off stars, it'll pull off dark matter from that satellite galaxy. And the material that gets pulled off ends up sort of roughly but not exactly, following the path of the satellite galaxy as it orbits in. So it typically in this stage, all of that material that gets shredded off ends up looking like it forms these tidal streams. And we can see, we see evidence for these tidal streams in stars. One of the most spectacular of these is actually from the Sagittarius dwarf galaxy, which is in the process of falling in and getting disrupted by our Milky Way. It hasn't gotten totally disrupted, so we can actually still see the Sagittarius dwarf, but we see the loops of the stars that it's left behind. So it's really quite spectacular, the fact that we can kind of trace out its orbit, and the information we can actually get from this is quite powerful. It places constraints on the Milky Way potential, for example. Oops. Now, we can ask, when you form one of these stellar streams, what happens to the dark matter that's also getting left behind? And so we can dig into the fire galaxies and find one of these mergers. We can look for the stream that it's left behind, and then see what happens, what the associated dark matter stream behaves like. And what we find in the examples that we unearth in these simulations is that in general, when you form a stellar stream, it also comes along with a dark matter stream. And the properties of those two, at least close to where the sun is, can be very similar, but they're not reproduced exactly. So for example, if you have a stellar stream of some given velocity, the dark matter stream may have a similar velocity, but it won't necessarily be exactly the same. But they're pretty good proxies for one another. Now we can continue evolving this. So when we imagine sort of like, the satellite galaxy has now made a bunch of different orbits around the Milky Way, kind of like winding a ball of yarn. So it leaves behind all of these streams, but the streams all end up getting wound up. And what you're left with at the end of the day is kind of like a massive cloud of stuff that's gotten left behind by this galaxy. And you might think that, okay, well, this is just going to wash out any kind of interesting information because it's all kind of mixed together. But that turns out to not be the case. And while spatially, most of the information most of the stars don't look very interesting, what you do end up getting, though, is that the velocity information is preserved from the satellite. And so we can, again, dig into these fire simulations, find examples of some of these mergers that have made numerous loops. And what we see is that both the dark matter and the stars that have gotten removed from these galaxies, excuse me, exhibit velocity substructures. So in different velocity coordinates, you end up seeing peaks and interesting shapes. And the stars and the dark matter from that merger actually reproduce each other's behavior very, very well. So that gives us optimism that if we are to find an example of this kind of merger in the Milky Way, we can very reliably infer the dark matter distribution from the distribution of the stars that we recover in the data. And lastly, I'll just note that the very, very oldest mergers, so the ones that came in very early on when our galaxy was just starting to be built up, have essentially had a lot of time to equilibrate. And when we identify the material that's gotten left behind from these mergers in the simulations, what we find is that the dark matter and the stars trace each other very well today, and that their distributions are essentially isotropic, following a Maxwell-Boltzmann expectation. So these very, very old mergers are essentially what we'd, when we assume that the galaxy is in a steady state, like this is essentially these very, very old mergers here. And again, what we're finding is that the stars and the dark matter from these old mergers are good proxies for one another. So based off of this work on simulations, that gives us a roadmap for how to actually tackle the problem of mapping out the local dark matter. So the idea is as follows. We can get dark matter near the sun either from material that's gotten left behind from satellite galaxies with stars, or from material that's left behind by satellite galaxies that don't have any stars in them. So these would be like much smaller, lower mass satellite galaxies that have fallen in. Now, if we focus on the left part here of the diagram, these satellite galaxies, depending on when they merged with the Milky Way, could leave behind a variety of different kind of structures. So the very oldest of these satellite galaxies would have left behind material that's equilibrated. The stars from these mergers would be really good proxies for the dark matter that also came from these mergers. As we move to the right here, then we get some satellites that came in a bit more recently. These will they won't leave streams, but they will leave velocity substructures, which we can identify and use to infer the dark matter distribution. And then the most recent mergers would be the ones that are leaving behind stellar streams. And in those cases, we do need to be a little bit more careful about how we infer the dark matter, the associated dark matter properties from the stream. So on the left part here, we have a roadmap for how to approach the problem. On the right is a bit more of an open question. It's not directly relevant now in terms of the data that we're getting from Gaia, because that's effectively stellar data. So that's a good probe for the left part here. But this remains important, and essentially is, as I'll argue at the end, essentially the next step for what we need to tackle in order to get the full solution for what the local dark matter distribution is. But let me now just walk you through how we actually approach the data analysis to recover information on the left part of this diagram. So that takes us to the Gaia data. So Gaia is the follow-up astrometric survey to the Hipparcos mission, which took place in the early 1990s. It was launched in 2013. The second data release was in April 2018, and probably sometime next year, the expectation is that we'll have the full third data release. The ultimate goal for Gaia is to provide measurements for over 1 billion stars, which is unprecedented. It's way more than we had with Hipparcos, and would essentially be a map of about 1% of all of the Milky Way stars. And by measurements here, I mean velocity, so you'd have positions of the stars, and you'd have the proper motions for the stars. And for a subset of this billion, you'd also have the full complete 6D phase space. So you'd have full 3D velocities as well as 3D positions. So this, at the end, by the end of the mission, is going to be a spectacular map of our galaxy. And to kind of put it in perspective, this is the Milky Way disk, but now rotated vertically. The Hipparcos mission was essentially looking within this small region here of the sun. That's where it had good accuracy on the stellar distance measurements. The comparable range where Gaia has the same accuracy is shown by this larger circle here. So you can see it's a dramatic improvement. And ultimately, Gaia is going to be able to measure proper motions out to this region here, which is kind of even off the diagram. So this is a big step forward in the quantity of data that we have, and it opens up a huge opportunity for understanding the dynamics for the galaxy. So what we're going to focus on is how we can actually infer something about the history of the Milky Way evolution from this data set. And so this is very similar to essentially going fossil hunting. So when you find a fossil, you use information about the shape of the fossil, its environment, and perhaps any kind of chemical, radioactive dating or something like that to infer something about the creature that it came from. What was the shape, what kind of animal was it? When did it live? Questions like that. We're going to try doing something similar here, except from data with the Gaia satellite. So instead of using the shape of a fossil, its environment, or radioactive data, we're going to use information about the positions of the stars, their velocity, their chemical abundance, to move from this diagram here on the left, which is the actual Gaia data, to an understanding of what this actual, to an inference of what, which galaxies that actually merged with ours at what point in time. Now, the challenge here is that the vast majority of the stars in this Gaia data set were ones that are actually born in our galaxy. So the stars that are here along the disk were not ones that were dragged in from these mergers. They were ones that essentially were born and evolved once our own galaxy formed. So those are not the ones that we actually want to use to do this exercise. But like I said, they make up the vast majority of Gaia's stars. So our task then is to really to dig into the data and to try to find the rare, there's essentially a rare events search, if you want to call it that. So we want to try to find those rare stars that we believe came from one of these mergers. So for all of what I'm going to show you next, I'm going to focus on the small region around the sun, the data from the small region around the sun. Obviously, we're focusing here because if we want to map the local dark matter density for terrestrial experiments, this is precisely the region that we need. And this is also perhaps the hardest region to do this exercise in because it's right in the galactic disk. And again, vast majority of the stars in this region were the ones that did not come from one of these mergers. So we literally are trying to look for a needle in a haystack here. Now, there hasn't been a lot of work really looking for these kinds of structures in the galactic disk, precisely because this is so hard to do. And the backgrounds here are so large. The traditional approaches that are typically taken when doing these kinds of analyses are to use certain characteristics of stars that are born in the disk versus stars that came from these mergers to distinguish the two, and then you place hard cuts on those. So for example, you expect that disk stars have very distinctive velocities or particular kinds of chemical abundances, and then you cut hard on those parameters to try to separate out the disk stars from the merger stars. That's kind of the traditional approach that's been taken. It's challenging though to apply these methods in the disk here where the contribution from the disk stars is so large. So what we want to do is see if we can develop new techniques to try to sift out these rare events. And so let me start by telling you of one technique that we developed that utilizes neural networks to essentially help us out in trying to identify the stars that we believe came from these mergers. So when you have machine learning, for certain kinds of machine learning problems, you train your neural network on a set of photos that are labeled. So in this case, if you're training your network to distinguish between a photo of a cat and a photo of a dog, you have a bunch of labeled photos of cats, a bunch of labeled photos of dogs, and you train your network to be able to distinguish between those cat photos and dog photos. So that after this training process, when you then apply the network to some random picture that you have, the network takes everything that it's learned and uses that to infer something about whether or not you had a cat or a dog. And in this case, it makes some prediction that what's in the laundry basket here is actually a dog, based off of what it learned from its labeled photographs. So if we want to apply this to the galaxy, what we need is a set of labeled photos that we can train the network on, so that we can then take that network and apply it to the data. And this is where having some of the remarkable advances that have been made on the front of simulations becomes really, really important. So what I'm showing here on the top is a simulation of a Milky Way galaxy. This one's referred to as an Anke. And on the bottom is the actual Gaia data. And so you can see by eye that the simulation, the mock galaxy on the top, actually does a pretty decent job at reproducing what we see in the data. So, you see, well, first of all, you see a disk that's formed in both. You see regions where there's a lot of dust. So these regions that are kind of dark here. And here is where there's a lot of dust and that's obscuring the light. And so for also the thickness of the disk is roughly comparable. There's a lot of similarities between the two. It's obviously not a perfect representation by any stretch, but the similarities are quite remarkable. And so the idea here is, can we train a network on the data from these mock galaxies to be able to distinguish between stars that it thinks came in from a merger and stars that it thinks were born in the Milky Way, and then use that to apply it to the Gaia data and then see what we get. So that's the general principle. There's a lot of ways in which you can think of that this would go wrong. And initially, when we first started on this project, I actually didn't think it was going to work at all. And the primary reason is, you'd obviously worry that the network is going to learn something that's very specific to the simulation, such that when it's applied to the real Milky Way data, it's going to just, its inferences are just going to be not helpful. But we did extensive testing on the set of simulation, the suite of simulations that we have, to characterize these biases. Discussing that would probably be a whole separate talk in and of itself. But suffice to say that as a result of these tests, we were confident that the network was not learning something very specific to the simulation itself. And so that gave us confidence for training the network on these simulations and then ultimately applying it to the data. I should also add that we use this additional transfer training step, which is often used in image processing, where you essentially retrain one layer of the network on a small subset of the actual data to just essentially kind of get it used to being applied to real data. And so we did that in this process to aid in helping the network in terms of inferring making better guesses when applied to the actual data. So let me show you what we found and what the implications are for the local dark matter. So what we get from applying this network to the Gaia data is essentially a list of stars that it thinks have a very high probability of having come in from mergers. And these are stars that are pretty close to where the sun is. What I'm showing on these panels down here in velocity space, so radial velocity, theta, and phi velocity relative to the center of the galaxy. The colors denote are just a heat map of where all of the stars are that the network thinks have come from these mergers. And there's actually a lot of structure here, which when you're just kind of staring at it, is hard to sort of denote. And we had to do some clustering algorithms to identify these more carefully. And so the results of those are shown by the lines. So let me break this down so that you can have a better understanding for what the components are that are contributing to the local dark matter. So the first is the pink, which is labeled as halo. So this component is essentially almost isotropic in each of these panels, which you can see from the fact that it's almost a circle. So that suggests that these are the stars that came in from very, very old mergers. So this is the oldest stuff that came into the Milky Way and then dumped stars near the sun. And based off of our work on simulations, we know that these old mergers would have also dumped dark matter, and that the velocity of those dark matter particles are probably very closely traced by the stellar component. The next thing that we find is shown here by the cyan curves. These have a very distinctive behavior in velocity space. So in some sense, it looks a little bit like a peanut here with these lobes in radial velocity, but not very much dispersion in angular velocity. And this blob, let's call it a blob, is actually something that had been discovered earlier in other parts of the galaxy with other analyses, and was identified as being one of the earliest mergers that would have contributed the vast majority of material in the inner part of our galaxy. And it's referred to as Gaia Enceladus. So this is just showing a video of the Enceladus galaxy as we think it would be acting as it falls into the Milky Way, gets disrupted, and then leaves all of its stars near the center. So the stars of Enceladus here are shown in red. The evidence for Enceladus merger, the papers that came out on this were almost immediately following the second Gaia data release. So this is work by Belokurov and Helmy and collaborators, and is a big shift in our understanding of the Milky Way's family tree. So if we come back to this diagram here, the discovery of Enceladus essentially pins us down to a merger that occurred about 7 billion years ago, probably at the time stellar mass of like 10 to the 7, 10 to the 8 solar masses for that Enceladus galaxy. And so from our analyses, we see that this merger left behind stars in the vicinity of the sun, which also indicates that it would have also left behind dark matter near us. And the velocity distribution of those dark matter particles, we believe, based off of our work on simulations, should be quite similar to the stellar distributions. And so this is the first indication that there's definitely a subcomponent to the local dark matter that is not in equilibrium, and that would have come in from a recent merger, in particular from this Enceladus galaxy. So this is the first place where we start seeing, with the addition of this new data, a divergence in our understanding of how we should be mapping the local dark matter based off of the standard halo model, which has been placed in place for a long time. And okay, so let's continue moving forward. So what we've had so far is a component that's the oldest mergers. Then we have this blue, which we think came in from this Enceladus galaxy. And what we're also finding is this distinctive blob here that's circled in neon green. And this one is, it's actually, there's a lot of stars in it. So it's about 200 stars, and they all have very coherent velocity. So it's very stream-like. And we're still trying to understand exactly what it is and where it came from. This is just a mapping of those 200 stars in position space. And so the little arrows just show the direction in which their velocity is moving. And you can see they're all kind of moving in the same direction. They rotate, they are co-rotating with the stellar disk, although moving a little bit more slowly. And they are on very eccentric orbits. So the kinematics of these stars are quite distinctive from that of the stellar disk, which is one reason that it could strongly suggest that these stars actually came from another galaxy merger that would have also deposited stuff near us. And you can see that the stars are just cutting straight through where the sun is. So if there is dark matter that's associated with this merger, it would, it may very well end up near where we are, near the sun's position. There's a lot of open questions that need to be resolved to really solidify whether or not this is a stream that came from a galaxy merger. And in particular, what's going to really help here is doing further spectroscopic studies of these stars. So looking at their chemical abundances and seeing how distinctive those chemical abundances are from stars that are in the disk. So this is ongoing work. The potential implications of this for dark matter are quite significant. So the types of galaxies that would give you a stream like Nyx are exactly the kinds of galaxies that had been posited over a decade ago to end up creating a rotating disk of dark matter in the Milky Way. So this image here is from one of these early works showing what one of these dark matter disks would look like, sort of this big puffy dark matter distribution around the stellar disk. And it would also be rotating along with the disk. So this is essentially it's a big difference from just thinking of a dark matter halo. In this case, we have a dark matter halo plus a rotating stellar disk inside of it. So one of the things that our group is working on now is just trying to understand how these disks form for galaxies that would have left behind a stream that looks like Nyx. And these are actually simulations that an undergrad in my group has been working on. In the left panel is dark matter that gets left behind from the merging galaxy. And then on the right panel are the stars that get left behind by the same galaxy. So the gray is our disk. And then the blob here is the galaxy that's falling in. And as I evolve this in time, you start seeing that the dark matter and stars that get left behind are essentially concentrated around the stellar disk and ultimately end up leaving behind their own kind of disky distribution of stuff. And you can't really tell this in this picture, but that disky distribution is also rotating around roughly along the lines of the rotation of our disk. So this is roughly where we're at right now. We've made a lot of progress on understanding the dark matter that would have come from these luminous satellite galaxies. So we now believe that there is a component of the local dark matter that would have come from very old mergers, another component that's coming from this more recent Enceladus galaxy. And we don't quite know yet what the story is on Nyx, but this is work in progress, trying to understand whether Nyx might actually be pointing to the fact that there is a dark matter disk in the Milky Way. I'll just note that there are currently some spectroscopic studies of Nyx that are underway. There was the telescope time for this was slightly delayed because of COVID, but there's ongoing work here doing observations of those stars. And then we're also trying to analyze a larger fraction of the Gaia data to see if we can find more candidates for the Nyx stream. So I'll just conclude actually by just mentioning quickly this last piece here. So I think this is a really fun application of machine learning. This was a paper that we just recently put out. So what we're we asked in this paper was whether or not we can actually use a larger fraction of the Gaia data. So pretty much all of the analyses I've showed you up until now, we're focusing on only less than 1% of the Gaia data, because less than 1% currently of Gaia has complete phase-space information, so all 3 velocity components. The vast majority of the Gaia stars, at least in the current data release, are missing a radial velocity. So if we can have a machine help us fill in this phase space for the remaining stars, then it would dramatically open up a much larger subset of the Gaia data that we can dig into and look for many of these patterns. And so we were able to achieve this. So we built a network that essentially takes in the 5D astrometric coordinates for the stars. So these would be position, distance, and proper motions, and then predicts the final missing velocity coordinate, and also outputs an uncertainty on its prediction of that velocity coordinate. So there's essentially 2 outputs here, line of sight velocity and then an uncertainty on that line of sight velocity. And one of the things we realized as we were working on this was that the sort of general framework of this network has, we think, quite wide applicability. You can maybe think of using it in like LHC type searches, where you also have, if you're producing dark matter, you have missing energy. And so can you use a network to actually predict something about the missing information that occurs in some of those analyses? In any case, we have not yet treated this particular application to collider searches, but we did find that this general approach actually worked really well for the Gaia data itself. And so this is just the last slide here showing and summarizing how it worked on mock data. So this is on the top here is just a distribution of the velocities for all of the young stars in the mock catalog. And the true distribution is shown by the cyan contours, and then the predicted distribution by the network is shown in the dashed white. Dashed yellow. And so you can see there's a really good correspondence between what the network is predicting and what the true distribution actually is. And then even in cases where we're looking at older stars where these distributions are much more complicated, the network again is doing a really nice job at being able to pick up all of the patterns in the data. So again, you see here that the yellow dashed and the blue nicely reproduce each other. So having essentially developed and tested this network on mock simulated data, we are now in the process of applying it to the actual Gaia data. And we anticipate that it'll quite dramatically increase the data set that we'll be able to work with. And so that's actually work that's underway as we speak, being led by my graduate student, Adriana Dropulik. And we're all quite excited to see what mysteries lie in this larger extended data set. Perhaps learning more about this Nyx stream, or perhaps discovering other kinds of structures that might be relevant for our understanding of the local dark matter density. So let me just conclude by just kind of summarizing how far we've come. So this is, the story began with flat rotation curves, and then based off of the observation of flat rotation curves came a series of works inferring information about how the dark matter halo is distributed in the galaxy. Those inferences relied on assumptions, in particular assumptions about how our galaxy is in steady state. And these are assumptions that we can now go in and actually directly test given the quality of simulations, given the quality of new data from Gaia, coupled with the advancements that have been made on the simulation front, as well as in different kinds of analysis techniques and machine learning methods. And so taken together, we've made some strides in identifying stellar substructures near the solar location. And then based off of what we've learned from studying the correspondence of stellar substructure with the dark matter, associated dark matter, we are started the process of being able to build an empirical model for the dark matter halo that accounts for these mergers and is independent of the assumption that our galaxy is in steady state. So we still have a lot of work left to do on this front, but I think that we now actually have a roadmap for how to tackle this question. And given the data, the upcoming data that's on the horizon, I'm optimistic that this is something that we'll be able to work through fully in the coming years. So with that, I'll conclude, but I'm happy to take any questions. Thank you.
Thank you very much, Mariangela, for this very nice talk. So I already see two raised hands. The first one that raised the hand was John March Russell. So John, please ask your question.
Thank you, Mariangela. A very interesting talk. I was confused about one thing you said concerning the dark disk issue. So I thought that the early Gaia releases had basically strongly disfavored thin dark disks. So could you say a little bit more about what kind of dark matter disk the Nyx possible merger might be favoring? I mean, and what the reasons are for behind that?
Yeah, that's a great question. So there's sort of two dark disks in the literature. Dark disks are used to refer to two different, essentially, well, two different origins. So there's the dark matter disks that would form in standard cold dark matter, which was what this early work by Justin Reed and Purcell and all was focusing on. So these would be dark disks that are forming from the merger of these CDM, like in CDM, just from mergers of these galaxies. And these kinds of dark disks tend to be pretty puffy. So they tend to extend quite a bit off of the galactic plane, which you can see from, I mean, this is an artist rendition, but you can sort of see it here, right? So this would be like the galactic plane, and this is definitely quite a bit off. Now, this is in contrast to double disk dark matter, and so like the work of Randall and Fan and Reese, where you actually change the dark matter model to allow for dissipative interaction. So then the dark matter itself can cool and collapse. So some fraction of the dark matter in the halo would cool and collapse to form a disk. Now, I will add the caveat that it's a big assumption that it forms a disk. It's actually not very well understood. This is a totally separate project that I'm working on, but if you sort of naively just assume that it does manage to form a disk and that disk is pretty thin, then you can place constraints on it with data from, well, Gaia and also like Hipparcos data, the older data set, Sloan and Gaia, because then it's the disk is essentially concentrated in this orange region here. And so because it's so the dark matter disk would be concentrated there, it would affect the vertical motions of stars in the disk.
So you have a much bigger Z dispersion in your disk.
That's right.
Yeah, okay.
Yeah, that's right. But the constraints on that one does need to be careful because it makes a lot of assumptions. A, that the disk should even form, which like I said is not actually very well understood. It also assumes that after the disk forms, it's aligned with the baryonic disk, because if it was misaligned, then none of those constraints would actually apply. Because you need the disk to essentially, the dark matter disk to essentially be like falling right along this line here in order to be able to constrain it.
Fair enough. Understood. Thank you.
Okay, next in line is Fabio Iocco. Please, Fabio.
Hi, Mariangela. Thank you very much. Hi, very nice talk. Thank you very much for the impressive amount of work. And I also appreciated very much the fact that, I don't know if it's intentional, you mentioned galactic cannibalism, and the first reference you have is to Hopkins. So that
yes,
quite impressive. So my question is the following: like you keep mentioning the local dark matter density.
Yep. Oh, sorry.
So my question is more about, the question is more related to, I think this is extremely exciting what you're doing, but I'm wondering, dynamically, even if you have a stream of whatever nature, the dynamical constraints that you infer through the circular motion of stars or the vertical motion of stars, up to current uncertainties in the data still stand. Of course, if you have a stream of dark matter that of whatever nature, of whatever speed you have, that would be dramatic for any other type of search that is sensitive to the velocity, to the speed of the dark matter. But whatever you're saying, it doesn't impact to more than a factor, or to less than a factor 2, probably, or a few, whatever dynamical constraint we have in the local density. And that's a question, it's not a statement.
Yeah, no, it's a great point. So one caveat, okay, so I agree with you if we take just at face value the constraints on the dynamical constraints on the local dark matter density. I mean, in that case, then we're essentially just, what this work is doing is saying, okay, given the total amount of local dark matter density, how do we essentially subdivide that and understand what's actually contributing to it? And how do we expect the velocities of each of those separate components to differ from, let's say, the standard HALO model? One thing that I don't think is actually very well understood, something that I've been thinking about a little bit, but it definitely needs to be fleshed out some more, is that the current constraints on the local dark matter density assume that the use genes analysis to essentially infer how much dark matter density is there given like velocity dispersions of disk stars. And those analyses assume that the stellar disk is in equilibrium. And that actually has now been sort of quite definitively disproven by the second data release of Gaia. So there's very evident ripples in the stellar disk of the Milky Way. And it's thought that vertical. Sorry?
You're talking about vertical velocities, or you're talking about the tangential component of the velocity?
It's in the vertical. You see it in the vertical velocities.
Yeah, I was thinking more
so if you look at the vertical velocities.
Yeah, I was thinking more about this. And I completely agree with you. When you go to the vertical velocities, that might invalidate the genes analysis. I'm totally.
Yes.
Yeah. However, if you take a face value, the analysis, the genes analysis, then there's big error bars that don't take directly that into account, but somehow they do indirectly. I was thinking more about the circular velocity analysis, and I never performed the calculation of how long it takes to perform an orbit around the sun, the galactic center, which I just did, and it's a time scale of something like 10 to the 8 years, right? So whatever you're measuring is something that is sensitive to variation averaged over 10 to the 8 years, and I assume your stream is faster than that. So whatever you're measuring, if the disk is stable, not in vertical terms, but in structure terms, then that dynamical analysis still stands, unless my brain is too slow to process this information right now.
So I mean, I need to think about that a little bit more. It's a really good point. I do think that the kinds of perturbations that people are considering for the disk, there's breathing modes to it. So I think it's not just in the vertical velocities, it's also in the radial velocities. So I think one would need to be careful because it would probably also impact this estimate as well. The thought is that these perturbations came from like Sagittarius flying through the disk and essentially just kicking it and then causing it to wobble. So yeah, I would need to think about that more carefully. I think in general, just it would be good to sort of understand more carefully how these perturbations to the disk end up impacting the inference of the local dark matter, like how sensitive like all of these estimates are to those kinds of perturbations, just so that we sort of have that clarified. Because if you look at it, there actually has been, at least last I checked, which was a few months ago, like no recent updates to local dark matter density from Gaia data. And I think it's precisely for this reason.
There is. Wait 1 week. But
oh, awesome. Okay, yeah. I'm really looking forward to seeing that then. Awesome.
Yeah, no,
great.
But I was hoping you had an answer to that. But we will stay in touch. Thank you very, very much for.
Yeah, I know. I'd love to continue talking about it. Yeah.
Yeah, let's do it offline. Thank you.
Okay, great. So I do not see any other questions. So, oh, sorry. There is a question by Rubakov. Please go ahead.
Yeah, my question is sort of the following: what sort of estimates are you thinking of? How much you expect to get deviations from the conventional, the standard dark matter scenario in terms of mass density or velocities, and in which way? Are they going to be larger or smaller? What sort of idea? Is it factor of 2? Is it factor of 10? Factor of 100? What sort of idea do you have?
Yeah, thank you for asking that. I had actually meant to mention this in the talk and then I forgot. There's actually an explicit reason why I have not shown one of those plots. That's partly because I don't think we're quite ready to, I mean, given all of the uncertainties yet and trying to understand where Nyx is coming from and things like that, we're not quite ready to sort of make a formal, here is the final version of the velocity distribution that should be used for all of these analyses. And so I'm always a little hesitant to show a plot like that, just because this is all still, there's a lot of work in progress. But that being said, I mean, I guess, so this is with caveats, obviously, based off of the fact that this is work in progress. In general, what we're seeing is that the velocities for the dark matter that would have come in from these really old mergers and also from Enceladus tend to be a bit slower than what you would predict naively from the standard halo model. This is ignoring any potential contribution from Nyx, which we have yet to sort of understand more fully what the implications of that would be. But if we take that initial observation and run with it, then that's essentially saying that you would be expecting to have fewer high-speed dark matter particles near, in your detector. And so that would essentially have the largest impact on searches for low mass dark matter. So for the WIMP case, it would be impacting the limits in the regime that's around like 10 GeV and lower. And in that regime, it could essentially, the limits could be like an order of magnitude weaker. It will not have as strong of an impact for heavier mass WIMPs, which are not relying on that high velocity tail to scatter. We have not looked carefully, but this could be quite important for axion searches where you're more sensitive to lower mass. With axion searches, you actually kind of want more lower mass dark matter, so that could impact more strongly the axion search sensitivities. So that's kind of where we're at now, given our understanding of the old mergers and also for Enceladus. It can change depending on what we ultimately end up learning about Nyx, because maybe the Nyx stream ends up populating and giving you some more of this high velocity dark matter that's there. So that's why this is still kind of work in progress, but at least in its current iteration, ignoring the contribution from Nyx, it tends to predict slower dark matter than you would otherwise expect from the standard halo model.
How about the mass density, local mass density of dark matter?
For the local mass density, that we haven't been able quite yet. We need to run the dedicated simulations that we're running will help elucidate that question. So, I mean, I think the best we have now is just what Fabio was talking about earlier, which is just from the dynamical limits and not from the work that we've been doing. But we might be able to do, we'll definitely be able to understand better the contributions of like Enceladus and the old halo component to the local dark matter density using some of these dedicated simulations that we're now running. So that's still to be determined.
Okay, thank you. Thank you for your nice talk. Thank you.
Okay. If we have time for another question, if there is any. I do not see any raised hands, so I would like to thank Mariangela once more for this very nice talk. And we will resume our program next week with the talk by Jure Zupan.
Okay.
So, Stefania, I don't know if you want to.
Just say have a nice evening or day or whatever. Thank you very much, Mariangela. Thanks a lot.
Thank you, Mariangela. Thank you very much again. Thank you.
I hope to see you here very soon. Ciao. Ciao a tutti.
Thank you. Bye.
Bye bye.
Bye.